Uh, Hi. Yeah, good afternoon, as Martin already said to everybody. So this is our group. It's myself, Ethan Martin, and Maren Summers and Alex Witt. And we'd just like to talk to you about hydrophobicity and philicity. So in this nanoscience camp that we did this summer, our first day we got here on Monday. Well, we got here on Sunday, but on Monday, our first actual class day and lab, we worked on superhydrophobicity and philicity. So, as the other group stated, that's when certain substances are attracted, where the water is attracted to those substances or repelled from those substances. So how we did this experiment on that first day is we took 4 copper plates and we sanded them down to remove the oxidation layer so that we had a clean slate to work with. And with that, we dipped it in silver nitrate to give it the nano roughness that we could build upon later in the experiment for, it to just actually work. That's like the building block, the nano roughness, that is. So we used 2 different chemicals. I don't remember the name, but I can tell you that one was nonpolar and the other was an alcohol, which is polar. As we know, it's an OH attached to a carbohydrate, excuse me. And so what we did is we soaked 2 of the different plates, those copper plates with the silver nitrate. We soaked 2 of those in the 2 different substances. And then we had 2 other ones that one we put hand sanitizer on and the other we left just plain. We, of course, rubbed it down with sandpaper and then left it as it was. And we put a water droplet on every single one of those 4 plates. In doing that, we saw that the one with the alcohol was super hydrophilic because it attracted the water, as the 2 were both polar, the water and the alcohol. So what that showed us is that, it had a greater angle than 150 degrees, the contact angle, and that showed us the superhydrophilicity. Excuse me, I mixed up the numbers. So that it was lower than 10 contact angle, and that's what showed us the superhydrophilicity of the alcohol. And then what we also did is we had the other substance, which was nonpolar, and we will put that on there. It formed the water droplet that was, of course, greater than 150 for the degrees for the contact angle. And the other 2, when we dropped it, were relatively close in contact angle, with one spreading out a little bit more and the other remaining more as a half dome, rather than the super hydrophobic, which was more of a perfect sphere, and the super hydrophilic, which laid as a puddle, as you'd see in the grounds.
In this picture, you see a boy sledding. So in the top left, you see him going down a steeper slope with a rough surface, and he's higher off the surface, which is indicating how the water was repelled. And then in the top right, the slope is still steep, but it's more smooth, and he's still repelled from the surface. And in the bottom left, it's a little less of a slope, and he's more attached to the surface, which would convey how the water droplet spreads out. And then on the bottom right, the surface is almost flat, and it's a little rough, so he's more stuck to it.
All right. So we start with the top left image. This shows super hydrophobic surface. So he's sledding down the hill, and the rough surface is repelling the guy sledding off the hill. So it's like the surface repelling water. The guy sledding represents the water droplet on the surface. The next image to the right on the top represents just a hydrophobic surface. So it's not as rough, but it still repels the guy sledding. And then the bottom left image is a hydrophilic surface. So as you can see, the angle of the hill isn't as great as the hydrophobic surfaces. So he's actually traveling slower as indicated by the dashing lines in the images before. There, he has none in this one. So you can see that he's traveling slower, so he's more attracted to the surface. And then the bottom right image, he is definitely not moving fast, as the hill's almost flat and it's very rough. So, I don't know if you can, so it comes up better there than we have the image here, but the angle is, for the top left, is greater than 150. So the angle of the hill represents the water droplet, the contact angle of the water droplet on the surface. And compared to the bottom right, you can see the angle is a lot less. So that shows it's hydrophilic. I don't know, do we go? All right, so I don't know what did we talk about next?
So what the artists didn't, they kind of conveyed all the concepts that we were taught here, but one thing was that with their contact angles, it kind of looks like here they're more doing it with the surface that the water was placed on, since it's seems like the water is the buoy and the surface is the snow he's sledding on. And so it looks like it's more measuring the surface, when with the hydrophobicity and hydrophilicity, you're measuring the contact angle of the water, not the surface.
And just adding on, one thing that I actually just realized now is that in the slope, as you see in the top left-hander, in the top left corner and the bottom right, you can see the bumpy, and that's supposed to be representing the rough nanoparticles that would be on the superhydrophobic and superhydrophilic surface. I believe that's all. That's all. Thank you.
So we had the water droplet on a surface, and depending on how hydrophobic or hydrophilic it was, the droplet would be more spherical or flat. Spherical being hydrophobic and flat being hydrophilic. So we would take a close-up image of that and then measure it with a protractor. You can other questions? No?
So the fancier $10,000 instrument that we use here is the same. It's not a camera.
It is the camera.
I mean, not a phone camera.
But it is just a camera.
Yeah. It is still a camera. And more stable than their hands, for example. And we can actually capture things that are really fast. Often you can track, literally, you can see the low speed of water vibrating. So, but yeah, it's $10,000 versus their phone. And you can see you are well spending on your phone.
I'm also going to say it's a lot harder to measure the angle with a protractor on the phone, because the angle on the protractor is a lot bigger than the phone, so it's a lot harder to measure the angle. So.
Okay, so I have two questions. And one is the same question that I asked last time, which is there's a rough surface on the bottom right and a rough surface on the top left. How would you differentiate, how could you modify this picture to differentiate those two rough surfaces? And also, the artist sort of played fast and loose with angles here. So there is something a little funny about the way the hill and the angle are related. So could you maybe explain that?
With telling the difference between the superhydrophobic and superhydrophilic surface, and at least in our experiment, the superhydrophobic surface was we dipped the copper in a chemical, the abbreviation for the chemical is DCT, and so the non that
So abbreviation's bad.
I can't remember.
What kind of chemical is it?
It was a nonpolar chemical, and so that repelled the water. And then on the bottom right, we used a polar chemical to dip the copper in, which made it superhydrophilic.
Any ideas on how you could change the picture to reflect that?
you could show different types of like kind of coverings on the nano rough surface, since that's what we kind of did to when we dipped the copper.
Or maybe on the bottom, like rock sticking out that the sleds could interact with. Sledding in bad seasons. But you see the idea I'm getting at. Okay, so the other question is, if you look at the top right and the bottom left, the ski slope is actually a very similar slope. But the angles are very different.
So one comment that I have is maybe the artist could have picked a side for the slope to go down, because it kind of, looking at it now, it's kind of a little confusing seeing that one way, you're going down the hill to the left, and the other way you're going downhill to the right. That might be confused with like supplementary angles.
They're mapping the ski slope onto a different aspect of the angle, so that a big angle of 110 and a small angle of 39 actually end up looking sort of similar in the picture, because they're not mapping the slope onto. In fact, the top two would be overhanging cliffs. The way that if you're mapping them all onto the slope. But it's important to bring this out because in a cartoon, people will visually take everything that's there. And so if there's a complication like that, you can actually lead people astray by making it simple. And so the one